Optimizer callbacks are functions that allow user-defined routines to be prompted to the optimizer to be executed during the optimization process. Callbacks are specific to a problem, and the method names start always with p.addCB. There are three types of callbacks. Output callbacks are called every time a new text line is written by the optimizer, and are commonly used for more detailed logging and reporting via the p.addCB message. LP callbacks are related to the search for LP solutions, and include, among others, the addCB LP log and addCB bar log, which are triggered at each iteration of the simplex and barrier algorithms, respectively. The highest number of callbacks available are the so-called MIP tree search callbacks. These are called at various points of the MIP tree exploration process, depending on the specific callbacks being used. For example, the callback function pre and sol is invoked every time a new integer solution is found at a node of the branch and bound process before the solution is accepted and saved for the algorithm to continue. To implement callback functions, users must follow three basic steps. The first is to define a function to be run whenever the optimizer reaches the specific point, which must receive a problem object and a data object. The second is to call the appropriate callback method and pass the name of the user-defined function as the first argument, followed by a data object. Then, the command optimize should be run, which triggers the appropriate solver. The callback function may therefore be run several times during the optimization process, and the data object is used to read and modify information within the callback. Multiple callback functions can be triggered at the same point of the optimization process, in which case they will be run sequentially according to an optional priority argument when calling the callback, such as in the example shown, where the function pre and to will be run first, since it is assigned a higher priority value. Callbacks can be removed from the problem by using the p.removecb method for that specific callback. If a function or data argument is passed, only the callbacks that match that attribute will be deleted. In case both arguments are passed as none or not passed at all callbacks of that type will be removed. This example shows an application of the pre and sol callback, where a user-defined function takes 4 arguments that will be passed by the optimizer. The function must return a tuple of 2 elements, as required by the pre and sol callback. A problem object is then created, and the problem is loaded from a file. Then, the callback is triggered by calling the corresponding method with the required problem object and a data object, which is assumed to have been defined elsewhere. The optimize command then starts the optimization process, which will stop at each node of the branch and bound, where a feasible integer solution is found to run the user-specified routine before accepting the solution found. The Python notebook named callback new node demonstrates the use of a callback function. In this example, a problem is read from an external file, and a callback function is used to store information for every node of the branch and bound tree during an optimization run. The run is stopped after a predefined number of nodes have been explored, and all nodes explored during the tree search are plotted after the solve. This example uses the problem.addCB new node method, which declares a callback function that will be called every time a new node is created during the branch and bound search. First, the storeBB node function is defined. Given a new node with a node number and its parent, we store the information in the left or right arrays depending on the branching direction, so that at the end of the branch and bound search we have the full tree node information stored in these arrays. Then, after declaring the required data objects for the callback function and for plotting, we specify that our function is to become a new node callback function with problem.addCB new node. This means that it gets invoked by the solver to allow our program to collect information at every new node that is created during the branch and bound search. The first argument must be the previously defined function, while the second argument is a user-specified data object, which in this case is not used by the callback function. Afterwards, 2 controls are set. The first control, named maxNode, limits the maximum number of nodes that are explored in the tree to 10. When exploring nodes using multiple threads, this limit may be violated as it does not represent a hard limit. Thus, we also set the threads control to 1 to limit the number of threads to a single thread, effectively ensuring that the max node limit is fulfilled when searching the branch and bound tree. After running all code cells, the output plot at the bottom of the notebook displays the nodes explored during the branch and bound search and their child nodes, numbered in the order of their creation during the search. We can observe that exactly 10 nodes have been branched on, as specified.